So last class we had the test, um, and before that we had just started talking about doing some example problems with the constant acceleration equations. So remember that stuff? So we introduced the constant acceleration equations. Those are the ones that are like v final is equal to v initial plus v initial times time final. Um, and I did a couple examples. Did anybody have any questions about the homework that I assigned related to that stuff? I think I did give 3 problems or something related to that. Yep. Oh, someone said that. Yeah. Let's go through it. Anyone have? I don't think I have the problems written out here. Thanks. Okay, number 7. Okay. A ball is rolled up a ramp um, with an initial speed of 4 miles per hour. Oh, this we got to do all these conversions. Um, so with a speed of 4 miles per hour, um, after 0.8 seconds, its speed is 1.5 miles per hour. And we want to know first, what's the acceleration? And second, how far did it roll in that time? And third, well, the third is a conversion. I don't know. Convert to kilometers. B to kilometers. Okay, so here's what's going on in this. So we have a first location. I'll call that location A. And the ball is sent rolling up the ramp. 0.8 seconds later, it gets to this point B. At A, it's going 4 miles per hour. At B, it's going 1.5 miles per hour. And if we call this t equals 0 at this location, then once it gets up here, t is equal to 0.8 seconds. Well, don't write that. Okay, so let's go through the steps of how to do problems like this. First, let's do the conversion. 4 miles per hour. So 4 miles divided by hours. 1 mile is 1609.344 meters. And 1 hour is 3,600 seconds. So can someone do that? 4 times 1609.344 divided by 3,600? Okay, so 1.788, and did the eights repeat or something? You don't remember? Okay, meters per second. And then 1.5 miles per hour. If you go through the same thing, what's that? 0.671 meters per second. And now we can go through the steps for the constant acceleration equations. The first one is we have to make those 4 choices. Our time equals 0 and our time final, we're going to make those decisions based on where we have information and where we want information. So what do we want to call our time equals 0? It's the first thing that happens chronologically where we have information. Right as it crosses A. So time equals 0 is when it passes that point A, or maybe I'll say that's when the speed is 4 miles per hour. And what do we want as our time final? It's the later instant where we have information. Yeah, when it gets to that second point. So when the speed is 1.5 miles per hour. And now we have to choose a 0 position, a positive direction. That's all. And these, you can choose anywhere and still do the problem. What do you want to choose as a position equals 0? Yeah, why not? So we'll choose that. And then the benefit of that is, so I'm going to write this as P is equal to 0 at the ball's location when time is equal to 0. And that has the effect of specifying that T initial is equal to 0. And then the positive direction, might as well choose the direction that the ball's rolling. So the direction of motion. So we'll call this positive. The second step, we want to just go through all of the, nice catch. We want to go through all of the possible variables, figure out which ones we know, which one we want. The total list of possible variables is time final, acceleration, P initial, P final, V initial, and V final. Time final. Do we know how much time has elapsed at T final? Yes. So T final is 0.8 seconds. Do we know the acceleration? Nope, that's what we're asked for. Do we know P initial? Yep, that's 0. Do we know P final? We don't know that. That's what we're asked for in part B, but for now I'm just going to leave that out because if we can find the acceleration without P final, that's all right for now. Do we know the velocity when time is equal to 0? Yes, that's given. So V initial is, did you say 1.78 meters per second? Oh, and what about the, I sort of gloss over this. That's the speed. Gave it to us as a speed. The velocity has the same magnitude, the same absolute value as the speed, but it could be positive or negative. So how do we know the sign of the velocity, of the initial velocity? That's right. It's moving in the positive direction, so this is positive. Yep. And then do we know the velocity at time final? Yep. Yep, that's right. So 0.671 meters per second. Okay, so we went through that whole list. This is what we want. These are what we know. And now we're looking for one of those equations, one of those 3 constant acceleration equations that has A in it, and anything else that shows up in that equation is known. Let's see. Is there one? I think this one should work. VF is equal to the initial plus ATF. So it says 0.671 meters per second is equal to 1.78 meters per second plus 0.8 seconds times A. I'll subtract 1.78 from both sides. Let's just make it 0.67. Okay, so 0.67 minus 1.78 is 0.11 negative. No, 1.11 negative, and that's meters per second. And that's equal to 0.8 seconds times the acceleration that we're trying to find. So negative 1.11 meters divided by seconds divided by 0.8 seconds is equal to A. And so A is equal to what's 1.11 divided by 0.8? Negative 1.38, and the units are meters per second squared. Does it make sense that the acceleration is negative? Yeah, because the velocity is positive, slowing down from 4 miles per hour to 1.5 miles per hour. If it's slowing down, velocity and acceleration are in opposite directions. And now the second part, we're trying to figure out how far it goes. Is there any reason to change any of these choices, the time equals 0, the time final? those will all work fine. The only reason that I can imagine ever having to change anything is if like the part B of a problem asks you for something that's happening at a different instant than one of your two choices from before of the times, you know, if it asked you how far the thing went zero point 0.4 seconds into the roll up the hill, then you'd have to change your time final to that point. Otherwise there's no way to calculate it. But all of our choices still work for part B. So time equals 0, time final, position equals 0, positive direction. We'll keep those the same. And what's nice about keeping all those the same, if you can, is then all the stuff you knew before, you still know. So we still know that time final is 0.8 seconds. From part A, we learned that the acceleration is negative 1.38 meters per second squared. Our initial position is 0. Our final position is what we're trying to find. Our initial velocity is 1.78 meters per second, and our final velocity is 0.67 meters per second. Okay, so is there an equation that has PF in it and anything else in it is known? I think the equation that we just used won't work because it doesn't have P final. Neither of the other two will, I think it looks like. So let's use this one. P final is equal to P initial plus V initial time final plus 1/2 A times time final squared. And so it says P final is equal to 0 plus 1.78 meters per second times 0.8 seconds plus 1/2 times negative 1.38 meters per second squared times 0.8 seconds squared. So what's 1.78 times 0.8? $1.424. Why'd we add the other significant figure? Just to make chemistry people mad. We have a seconds in the denominator and a seconds in the numerator, so those cancel. So this is meters. Okay, and then what's 1.38 times, to square this, that's 0.64 divided by 2.
Negative 0.442.
442. And that's also meters because you have a seconds in the denominator here that cancels with seconds in the numerator. And what does that come out to? P is equal to 1, no, 0.82, no, 982, 982 meters. Any questions about that one? And then part C is just to express that in kilometers. 1 kilometer is equal to 1 times 10 to the third meters. And so 0.982 meters times 1 times 10 to the third meters over 1 kilometer is 0.982 times 10 to the minus third kilometers. And that is 9.82 times 10 to the negative fourth kilometers. Any questions about any of that? Okay. Now we're going to talk about really the most important reason that these constant acceleration equations are important. The most important use of the constant acceleration equations. And that is free fall and projectile motion. And I'm going to just from now on call free fall and projectile motion free fall. They really are the same thing. It just depends on what the initial velocity is. But the definition of free fall and projectile motion is an object that is only acted on by one force. So an object is in free fall or projectile motion if the only, and let's say significant, if the only significant force acting on it is gravity. And so what we're going to be talking about now are objects that are moving through the air, and the only force acting on them is gravity. So they're not touching anything, and there are no significant air effects, no significant air resistance. And we'll talk about that assumption later today. But this gets to the first major misconception that I want to talk about in this class. And there are going to be a few of these as the class goes on. This is the first thing that probably, so, we're talking about objects flying through the air and rolling and whatever in this class. And with most of these things, you have an intuition that you've built up through your life that helps you kind of understand what's going on. But there are a couple of places where we're going to talk about stuff where you do have intuition, but the problem is your intuition is probably wrong about it. And so these are the things where we're not just going to have to explain how it works. We're going to have to go back and try to do some erasing and then fill that gap in your mind with the real stuff. Okay, so this is the first one. This is the first erasing that we have to do in your brain. Major misconception number one. Most people have the mistaken impression that gravity makes heavy things fall faster than light things. Um, and that makes sense with a lot of what we're used to seeing. I mean, everybody can accurately predict what would happen if you took a bowling ball and a feather and dropped them off a building. You know, the bowling ball would hit the ground, and a long, long time later, the feather would flutter down to the ground. And um, the idea that it has something to do with their masses or their weights is not totally off, but it's not gravity that makes that happen. So, what really is the case um, is that it's just air effects or air resistance that makes some objects fall differently than others. Um, in other words, it should be the case that if you in a perfect vacuum got all the air out of what a vacuum means is you suck all the air out of somewhere, and if you do that, you should get out first because you can't breathe if there's no air, and also your all of your organs and head would explode because you have a high pressure inside and the low pressure outside would. So be careful if you do this. But if you're in a vacuum and you drop a bowling ball and a feather at the same time in a vacuum, they they should fall exactly the same, hit the ground exactly the same. And it's a sort of a famous video from the moon landing that an astronaut does it with a hammer and a feather, and it looks like it works, but it's pretty grainy video. Um, so uh, there's a recent video. I think it's not MythBusters. I don't know what it is. But I'm going to show it right now, where they actually go to a building that's used for aerospace experiments. Um, it's a gigantic, huge, like building that they can suck all the air out of, and they actually go and do this, and they drop a bowling ball from the ceiling and a feather from the ceiling. First, they do it with all the air in there, and it does just what you'd expect. The feather just flutters down long after the bowling ball smashes into the ground. But then they spend they say like a couple of hours or something sucking all the air out of this building, and they drop them again, and they just boom, smash into the ground. The feather hits the ground and bounces up into the air. It's really cool looking. So I'm going to show this video and just remember the connection to this. Major misconception number one. You have to delete the part of your brain that thinks gravity wants heavy things to fall faster and remind yourself that it's really just air resistance that makes certain light things fall more slowly. Okay. Even like the ancient Greeks, like some of the people who we, think of as like the smartest, most important scientists and philosophers uh, in, Western civilization, um, they hadn't realized this yet. They still thought that heavier things um, are pulled down more quickly by gravity um, than lighter things, and that has something to do with the way that gravity acts on things. It started to be figured out by Galileo in like the late 1700s, I think. Um, but yeah, it's a big idea. So uh, the question then isn't really um, like when you're thinking about what things fall one way and what things fall another way, and how can you predict it, the question isn't really how does gravity act on different things. um, Gravity acts exactly the same on different things. The question is, what are the things that determine the effect of air resistance on an object's motion? What objects' motions are strongly affected by air resistance and what are not? So the real question is, what objects, no apostrophe, objects are strongly affected by air resistance and what objects aren't. Um, okay, so we're going to talk about three basic things that determine how much air resistance affects an object's motion. Um, so there are three main contributors to how much air resistance affects an object's motion. Um, the first one is the object's mass. So, like I said, it's, people sort of have this commonly held view for the most part that heavier things are accelerated down to the ground more by gravity than lighter things. And it comes from the fact that air resistance, if all other things are equal, air resistance is going to have more of an effect on the motion of a lighter thing than a heavier thing. Okay? So like a bowling ball, air resistance, if you drop it 10 feet or whatever, air resistance has almost no effect on it. Um, so the first thing is the object's mass. Um, if everything else is equal, air resistance affects the motion of lighter things more than heavier things. Um, and an example of this, think about, I don't think this one takes too much convincing, but, imagine going up to the top of a building and dropping like a metal pinball and a ping pong ball. Say they're the exact same size, they're the same shape. So the only things different about them are that um, the pinball is a lot heavier than the ping pong ball. Um, um, since the ping pong ball is a lot lighter, air resistance is going to affect its motion a lot more. And so the pinball is going to hit the ground a pretty long time, a second or whatever, before the ping pong ball will. And if there's a strong wind, it affects it more. So the pinball would hit the ground first. Um, the second thing that determines the effect on the motion is, we'll think of it as surface area. And it's a little more complicated than just an issue of surface area, but I think that's a good way to think about it. So if everything else is equal, air resistance has a bigger effect on an object with a larger surface area. There's just more room for the air to make contact with it. So to think about this, imagine dropping like a toy army man with a parachute, off a building at the same time as you drop like a ball or something that has the same weight. So like a parachute, toy soldier versus a ball with the same weight. Um, what a parachute actually, the reason a parachute works is because it uh, it gives the person who's jumping all this extra surface area to catch the air, and that's why it slows you down so much. So uh, the ball would hit the ground fast, and the toy soldier would, slowly come down. And then the last thing, and the one that has the biggest effect, is the speed. Um, so if everything else is equal again, um, a faster moving object A faster moving object's motion is more affected by air resistance and as an example of that, and to see how big an effect the speed has, um, think about you know, rolling down the window, putting your hand out the window. Like, think about, or when you leave today, try doing it. As you're going through the parking lot, you don't feel anything, right? You don't feel, but if you do that on the highway, it's a lot of force pushing against your hand. It's hard to hold your hand in place. That's the difference in the air resistance effect that you get going from 5 miles an hour to 55 miles an hour. Um, and I said that speed is the one that has the biggest effect. Um, that's because in the equation that factors all this stuff in, everything is just multiplied. There are terms that there's a term that represents the surface area, and not a term, a factor. So it's all multiplied together. So there's one that represents the surface area, one that represents the mass if it's a falling problem, but then the speed comes into the equation squared. So if you double the speed, it multiplies the air resistance by 4. If you multiply the speed by 10, it multiplies the air resistance by 100, So it has a huge effect. Yeah.
What you mean by it has, like, it has a bigger effect on the air, so the bigger the surface.
Right. So like if you just drop two things, the one with a small surface area will hit the ground a lot closer to what it would if there was no air at all. Like what a bowling ball does. Like whether there's air or not, the bowling ball smashes into the ground. It takes about the same amount of time. But the feather has a lot of surface area. Like that's what feathers are useful for, is having all that air, is that ability to catch the air. And so there's a lot, air resistance slows the feather down a lot. That's why it drifts down slowly. Um, okay, so um, all of the free fall calculations that we're going to do assume that air resistance is negligible. Um, so all our free fall calculations are going to assume air resistance basically isn't there, is negligible. So when is that assumption reasonable? Um, well, assuming that there's no air resistance works well if you have things that are fairly heavy, small, and slow. and it works badly if you have things that are relatively light, spread out, large and fast. Okay, so something that is pretty dense, like any kind of metal ball or a rock, uh, um, and that isn't going super fast, this approximation will work well. The sport in the Olympics where the big, huge guys throw the shot put, 16-pound steel ball. They spin around and grunt and throw this ball, and it goes like uh, 70 feet or something. Okay, so if you throw something 70 feet, it's never going that fast because that's not really that far. Um, and it's a very dense ball. And so if you do the calculations, if you measured the angle that it was thrown at and measured the speed that it was released at and used the assumption of no air resistance to calculate where it's going to land, you would be accurate to a huge, like a lot of significant figures. It would be basically perfect, that calculation. But if you try doing it with, say, take a beach ball and imagine somebody throwing a beach ball as fast as they can, and you measure how quickly that leaves their hand, and the angle that it leaves their hand, the the way that we're going to do calculations would give totally garbage answers because it's big, spread out, it doesn't weigh very much, and you're throwing it way too fast for air resistance to be um, negligible. Okay. Uh, let's stop there for tonight. And so we'll do the quiz, the lecture quiz, and then that's it.